So here's the cool thing. We know we can find the area under velocity curve to figure out distance traveled. We can find the area under any rate curve to find out how much the original function has changed over that time interval. So this is an example. The production rate of cola in thousands of gallons per hour is shown in this graph. To the nearest round number, how many thousands of gallons of cola were produced that day? So this function, I could call it C. Well, I might call it C prime. If C is the amount of cola produced, then this is C prime, the rate at which cola is produced. If I want to know how much cola gets produced from 0 o'clock in the morning, which we'll call midnight, until midnight the next morning, I can find the area under the curve. As long as I figure out the units correctly, that's going to give me the amount of cola produced. So this isn't necessarily a RAM or any kind of rectangular approximation problem. This did show up on an AP test though. So notice this time, since nobody specified to approximate the area under the curve, I'm just going to count boxes. There's 1, 2, 3, 4, 5, 6 whole squares, rectangles if you will, that are under the curve. That's 6. 7, maybe if I add that to it, it makes 7. And here's 8, maybe if I add that little piece of a rectangle there. So now I have 8 rectangles. Each one is 6 hours wide. So 6 hours. And how tall is each one? That's 100. Standing in for 100,000 gallons. And now I'm just finding the area, so I'm going to multiply. So 8 times 6 is 48. 100,000 gallons of cola. 1,000 gallons of cola got produced on that day in July. So here's another problem. This time, you've seen this problem before. I have a balloon. The radius is expanding, so the volume of the balloon is expanding. And I know something about r prime of t. I know how fast the radius is changing, at least at these certain time values. The question I want to know is, over the time 0 to 12 minutes, how much does the radius grow? So essentially what I want to do is find the area under the r prime curve. Of course, I don't have an r function that I can look at, but I can use rectangles to approximate, and I've been instructed to use RAM. And here it doesn't say, so we're going to use the intervals specified in the table. So I'm going to use the interval 0 to 2, the interval 2 to 5, 5 to 7, 11 to 12. I'll write it up. So here's my answer. This is where this comes from. I have one rectangle that covers 0 to 2, so it's 2 minutes wide, and its height is 4. So 2 times 4 gives me the area of the first rectangle. My second rectangle covers 2 to 5, that's 3 minutes wide, and its height is going to be 2, so that's how I have 3 times 2. My third rectangle covers 5 to 7, so its width is 2 minutes, its height is 1.2. My next rectangle has a width of 4 minutes from 7 to 11 and a height of 0.6. And then I have one last rectangle who has a width of 1 and a height of 0.5. So you would add this all up and get the change in the radius. So the change, that's each rectangle is feet per minute times minutes. So the minutes cancel out. And my answer is going to be in feet. So here's my final answer. These all add up to 19.3 feet. So I would say the radius of the balloon increases by approximately 19.3 feet over the time interval 0 is less than or equal to t, which is less than or equal to 12. I have to write in my equal signs because I don't have a typewriter that does it.